Okay, so continuing, if the voltage and resistance is related according to this equation, the question then is, how much resistance does something have? And it turns out the resistance is a property of what the material is made out of, because some things are good conductors and some things are less good conductors, and therefore some things will have more resistance than others to the flow of charge. And it also depends on the shape and like how fat it is, how much room there is for it to move through, whether it's very long. Again, using the hallway analogy, if we have a hallway with a lot of people in it and that hallway is really long, you're going to experience more resistance getting through the hallway than if it's a very short hallway. Same thing, if same number of people but you make it very wide, there's going to be more room for you to move. Now, again, analogies are not perfect, so be careful thinking of it exactly that way, but it gives you a good idea of a way to remember it. So what we're going to do is we're going to talk about an actual physical device. So if I took, for example, a wire, and I knew that wire has a cross-sectional area A. So, uh, and I want to figure out if I applied a voltage here, I would get a current to flow. So if my voltage is applied across the ends of this piece of wire, I would get a current flow, and I would then be able to, from knowing how much current is flowing, I could calculate my resistance by watching V over I. So given an applied voltage and measuring the current that appears in that section of wire, I could know its resistance. But if I change the shape of the wire, if I go from that wire to a little thin wire, and I do the experiment over again, I am going to get a different resistance value because I applied the same amount of voltage, but the current that appeared is going to be different because this second wire is much more constrictive. The cross-sectional area for the wire to the current to flow through is much tighter. Therefore, given that it's made out of the same material, you're going to have a much higher resistance. So we need a way to represent this resistance based off of the shape and size and material the of the of the object that we're interested in. So we introduced this concept called resistivity. It's represented by the Greek letter rho, and so there's a derivation in the text about where rho comes from if you define it in terms of the electric field and the current density. But I think the easiest way to think of it is it's just an intrinsic property of the material. So rho for copper is different than rho for silver, and it's different than rho for steel, and it's different from rho for other things. So it's an intrinsic property, sort of like density or things like that. So we think of this then, rho, as the resistivity. And to calculate the resistance of an object, we need to know what it's made out of. So that's going to be its resistivity. Things with higher resistivity are going to have higher resistance. That's why there's a direct proportionality here. Times L, the length of the object, divided by its cross-sectional area. So length and cross-section. And I hope that this makes some sense to you. If I make the object longer, there's more of the current that the current has to pass through. It's going to get more resistance. If I make the object wider, it's easier for the charges to get through there, and so the resistance would go down. So the resistance of an object is equal to rho L over A. This is true for conductor type objects like wires and carbon resistors and other things like that. This is kind of a general term for calculating the resistance. So this rho value is something you would look up in a table. So rho, there are tables of this data compiled by standards institutes. So they'll have tables of what's the resistivity of copper, what's the resistivity of silver, and all things like that. But the thing to remember is that this rho value is temperature dependent. So if you know the rho of copper, the resistivity of copper, which I'm just going to see if I can find one. Hold on a second. Here's the resistivity of copper. You'll see it's rho sub 0, meaning that this is the standard value at 293 degrees Kelvin, or 293 Kelvin. The, the value will change if we change the temperature. So we need a way that if we knew the standard is at 293 Kelvin, or 20 degrees Celsius, if the room that you're in doing the experiment was 23 degrees Celsius instead, you would need to adjust your resistivity values. Or if the wire is warming up because there's current flowing through it and it's getting hot, and the wire itself is at 300 Kelvin, then you would need to adjust your resistivity to get good results. So we need a relationship that relates resistivity with temperature. And so that relationship is given by rho minus rho 0 is equal to rho 0 times alpha T minus T0. T0 is the temperature that you know rho 0 at. So if you're looking in a text for standard rho zeros, this T0 would be 293 Kelvin, because most of them are quoted at 20 degrees Celsius. And then this T would be the temperature that you're looking for rho at. And then this one is your new value of rho. So you'll notice that the last thing here left is this alpha. And that's not a proportionality symbol in this case. That alpha is the temperature coefficient. For your material. So not only do these standards organizations classify and measure the resistivity value of each material, they also measure the temperature coefficient of each material so that you can then calculate the resistivity of your particular metal at any temperature in which you're working. So for copper, that temperature coefficient would change then, or would allow us to change the value of resistivity as temperature goes up or down. Now finally, we need to talk about what happens to the energy of this circuit. If we think about it, this battery, if I think about the battery over here, and it's got a negative side and it's got a positive side. So that means that chemically internal to that battery, there's a chemical reaction that's taking charges and lifting them up in electric potential. So we usually think of the negative side of the battery as having a potential of 0, V equals 0. And we think of the positive side of the battery as having the potential plus V. So if this was a regular battery, this might be 1.5 volts. So the chemical reaction inside there is adding energy to the charges by taking away energy from the chemistry of the battery. So I have these charges up here that are at a higher potential. They have a potential energy, therefore they can do work for me. The way I let them do work is I connect this battery via a conductor, which we represent as having resistance. Remember, we just showed that a metal has resistivity. So even if I just took a wire and stuck it from one end of the battery to the other, that wire would still have some resistance. So suddenly, as soon as I made that connection, a current would begin to flow equal to V over R. And the question then is, if the chemistry inside this battery is adding energy to the charges, as the charges work their way around this circuit and end up back at V0, they've had a net voltage change of minus V. Well, when charges have gone down in potential, we know that a charge falling through a potential, its potential change, delta U, is going to equal Q delta V. And so this charge, as it's moved around the circuit, has had a negative delta U. In other words, it has done work and it has given up its energy. So the question is, where did that energy go? It can't just simply disappear. So we know from conservation of energy that if one part of the system is is adding energy, then another part of the system has to be taking it away so that energy is not just being created or destroyed. So in our case, this resistor right here is dissipating energy. We refer to it as dissipating energy. It's going to give off that energy as heat. So our electric energy that we lose gets turned into heat energy by this resistance. And from a microscopic standpoint, you can kind of think about that from way back in our conversation. We were talking about these charges banging their way down this wire as the conduction is happening. Well, every time one of these charges reflects off of one of these charge carriers, uh, there's a change in momentum there, which means there's a momentum transfer to the the ion that's in the or the charge center that's in the metal. And so some of that energy is going to get given up to the vibrational energy of that charge. And we know that vibrational energy in a material is related to heat energy or temperature. So as the electrons or the charge carriers work their way down the wire, they're constantly banging into the lattice of the metal and transferring kinetic energy into the vibrational energy of the lattice, and therefore it's heating the lattice up. Then at the surface, of course, as the material heats up, it's going to attempt to reach equilibrium with its environment by transferring energy off into some sort of radiative power. And so, although we're constantly pumping in electrical energy, the resistance is constantly taking electric energy out. So, the question then is, how fast does that happen? And we know that the rate of energy loss or gain we like to refer to as power. So, power is equal to, in an electric circuit, is equal to I times V. This is true whether the power is going in or out. So if you know the current and the voltage, so if I know the current flowing through a battery, I can know exactly how much power the battery is adding to the circuit, the rate at which it's adding energy to the circuit. If I know the current and the voltage across a resistor, I know exactly how much the rate at which energy is being removed from the circuit by the resistor. And in our very simple circuit that we just drew, where we have only two elements, there's positive IV worth of power taking place from the battery, and there's minus IV worth of power, which makes sense. The total rate of change of power or the rate of change of energy for the entire circuit should be zero for conservation of energy to be true. Which means then we can apply from this equation, we can rewrite it using Ohm's law. So I could, for example, put in what V is equal to. V is equal to IR for a resistor. So I can say that the power loss in a resistor is I squared R. So if I know the current flowing through a known resistor, I can calculate how much rate at which its energy is being dissipated by I squared R. You can rearrange this equation in other ways too. You can do P is equal to V squared over R if you know the voltage as opposed to the voltage change at the resistance instead of the current through it. So these three equations can all be useful for calculating power loss at any place in a electric circuit. Okay, so the next portion of these series of videos will be some sample problems showing how some of these concepts can be used to make calculations of circuits and resistivity and other current and resistance related materials.